Hello everyone, welcome to this session on ROC curves. We'll see how the ROC curve can be used in performance measurement of a model, and to be more precise, we'll see how we'll represent confusion matrices on the ROC curve such that we could pick out the right threshold for our given task and also even the right model for our given task. Let's get started. In order to better explain the receiver operating characteristic plot, we are going to consider a very simple example of a Twitter algorithm which takes in a given number of hit words and says whether that information or that tweet is a sensitive tweet or not. Right here we have data points representing the non-sensitive tweets, and here we have data points representing the sensitive tweets. Clearly you could see that where we have more hit words, those tweets are flagged as sensitive. Now actually in real life you wouldn't have this kind of simple inputs like say just counting the number of words, because with a simple algorithm you could always use a number of hit words and then see whether it's sensitive or not. But then to make this easy to understand, we're going to use this very simple example instead of maybe an example where you have an input which is say a video, an image, or some unstructured text. Now we are having this right here which represents our data set, and then we suppose that we have our model which we call model A, which has the following predictions. So here are the actual values, and then we've trained a model which makes use of this data set and does these predictions right here. Now as you could see, we have this points, so we have this given number of words, and for this model A, when this model A gets this number of words, it predicts a value of about 0.1. so 0.1 that's falls under the non-sensitive region. If we consider a threshold of 0.5, we have this next one right here just above 0.1, this next one that's around 0.25, this next it's at 0, so all of this is non-sensitive. But then we have this point right here, that's we have this data point which is actually meant to be sensitive, but the model predicts it as non-sensitive. And then for the rest right here we have this one which is predicted as sensitive, but a value of about 0.75, this a value of about 0.75, this one just above 0.5, and this a value of 1. Now based on this model's predictions, we have 4 true positives. We could count them. We have 1, 2, 3, 4, because the model predicts them as positives and they are actually positive. Now we have no false positive because there is no prediction here, as you could see, which is a positive when it's meant to be a negative. Positive is supposed to be sensitive, and then negative non-sensitive. True negatives we have 5, as you could see. We have 1, 2, 3, 4, 5 which are predicted as negative and which are actually negative. False negatives we have 1, we have this one which is predicted as negative but which is actually a positive. So that said, using the threshold 0.5, we have a true positive rate of 0.8 using this formula, and then we have a false positive rate of 0 using this formula too. Now once we have the true positive rate and the false positive rate, we come back to our ROC plot where we have true positive rate against the false positive rate. So we plot 0.8, or we plot at the point 0.80, this right here. So this is the point 0.8, so true positive rate 0.8, and then false positive rate 0. That said, we now move to another threshold. So in this case we suppose a threshold of 0.2. As you could see, we have a no threshold of 0.2. That's it right here. We have now 5 true positives. 1, 2, 3, 4, 5. We have 2 false positives. 1, 2, because these 2 are being predicted to be positives when they are actually negatives. We have 3 true negatives, 1, 2, 3, and we have no false negative. So we have no prediction, or we have no value predicted to be negative when it's actually positive. Now that said, we have a true positive rate of 1, we have a false positive rate of 0.4 using these formulas. I'm plotting that, we get this right here. So we have 1 true positive rate and 0.4 false positive rate. Picking up another threshold, that's 0.25. we see right here we have true positives, that we have 5 true positives, we have 0 false positives, we have 0 false negatives, we have 5 true negatives, and here we have a true positive rate of 1, a false positive rate of 0. So here's our point right here. Move to the next threshold, that's 0.75. we have 3 true positives, 1, 2, 3. We have 2 false negatives, this 1 and this 1. We have 5 true negatives, this 5 right here, and we have 0 false positives. So that gives us a true positive rate of 0.6 and a false positive rate of 0. There we go, we have 0.60. Now you should note that this, or to come up with this plot right here, we should be able to take in a good number of thresholds ranging between 0 and 1, as the aim of this whole process is to look for the most appropriate threshold, that is that threshold which permits us have the highest possible true positive rate while at the same time having the lowest possible false positive rate. In this example, we see clearly that our best threshold would be 0.25, and that's thanks to this ROC plot right here. Nonetheless, it's important to note that your ROC plot will not always look like this. That is, you wouldn't always have a situation where we have the true positive rate maximized and the false positive rate minimized to the lowest possible value, that's 0. In some cases, you would have a true positive rate, or the highest possible true positive rate you could have is 0.8, and maybe the lowest possible false positive rate you could have is 0.1. And so this serves as some sort of dashboard where you just look at it and then you spot that given point where your model gives out the best possible results for your use case. Now coming back to the Twitter use case, you'd see that Twitter could afford to have non-sensitive information flagged by its model as sensitive, but it wouldn't want sensitive information to be flagged as non-sensitive. This simply means that Twitter would want to minimize the number of false negatives even at the detriment of the number of false positives. So that means Twitter would want to maximize the true positive rate. That's simply because minimizing the false negatives means maximizing the true positive rate even at the detriment of the false positive rate. So if we had a plot which looked instead like this, that is without touching these points, so if we had this kind of plot, Twitter will prefer to use this particular threshold right here, since it maximizes, or we have a true positive rate of 1, even though the false positive rate isn't 0. And in cases where you would want to put some priority on the false positives, that's if you want to minimize the number of false positives at all costs, then you would want to choose this point right here, or this point where we have a given threshold right here, such that the false positive rate can be minimized to its lowest possible value, and in this case is actually equals 0, even though the true positive rate isn't taking up the value 1, or the highest possible value you could take. That said, one good news is with most deep learning or machine learning libraries, you will be able to generate this ROC plots automatically, so you don't have to pick out each and every one like this. So once your model has generated, or once your model has been trained on a given data set, and then you want to evaluate your model, you could just come up with this ROC plot, and then based on your initial requirements, you could pick out a threshold which suits the most. Apart from the fact that thanks to the ROC plots, we could select the best threshold based on our initial requirements. We could also use the ROC plot in comparing several models. And right here we have this model B, where this model A, model B, and then this model B has the following predictions. You see that model B's predictions are quite different from that of model A. And so with a ROC plot like this, we'll be able to compare this to models. We see with model B we have the threshold 0.5. We could compute the total number of true positives. We have 1, 2, 3, and then we move to the false positives. We have 1. The false negatives we have 2. It's 1 on this. The true negatives we have 4. 1, 2, 3, 4. This gives us a true positive rate of 0.6, false positive rate of 0.2. So we could plot out that simply like this. We move to the next threshold 0.2. We have 0.8, 0.6, 0.8, 0.6. The next threshold 0.25. We have 0.8, 0.4, and then we have 0.75, 0.4, 0.0. So this shows us that our model B's ROC plot will look like this instead of what we had seen previously with the model A. And since from our requirements, our aim is to maximize as much as possible the true positive rate, we'll then pick out this point right here, since at this point we have the highest possible true positive rate and the lowest possible false positive rate based on the or comparing the highest possible true positive rates. So if we compare these 2 points right here, which would have a true positive rate of 0.8, you would see that the false positive rate is minimized at this point right here. So we would prefer to work with this threshold right here, which turns out to be 0.25 instead of just a default threshold of 0.5. That said, we could have this 3 ROC plots. Here is that of model A, and this is that of model B. We see clearly that model A is a better model simply because model A permits us have the highest possible true positive rates while also having the lowest possible false positive rates. Unlike model B, whose positive rates or the highest possible positive rate we could get here 0.8, even though we could have a false positive rate of zero. But having a false positive rate of 0 is very detrimental to the true positive rates, since at 0 false positive rate we have a true positive rate of only 0.4. So we can pick this point right here. And from this we see that the ROC plot is some sort of dashboard where we could clearly and easily pick out the right threshold values and then compare different models with each other. This video is inspired by a question posed by Dylan on the Deep Learning with TensorFlow 2 course. If you want to get a scholarship for Deep Learning with TensorFlow 2 course, all you need to do is to make use of a simple classification data set, use a machine learning library like scikit-learn, and then do a very simple ROC plot. Click on this link right here, and then depending on whether you're a single learner or you're coming in a group, you could simply apply for a scholarship with your generated ROC plot attached. So wish you the best and see you next time.